Section 4.4, Conversion between number bases, Part 2. We're converting from decimal form to another base. Divide the decimal numeral by n, the new base number, and record the quotient and the remainder. Divide the quotient by n and record the remainder. Repeat step 2 until the quotient 0 appears. Write the remainders in reverse order. This is the new number in the new base. It is a lot of dividing and remainders. We have to organize our work so we have it all ready to go. We're going to convert 7,508 from decimal to base 7. Our first division is going to be 7,508 divided by 7. I'm going to organize my divisors and my remainders to the right, my long division on the left. 7 divides into 7 one time. 7 divides into 5 0 times. Oops. 7 divides into 50 7 times. 7 divides into 18 2 times. Remainder 4. We're going to do 1,072 divided by 7. 7 goes into 10 once. 7 goes into 37 5 times. 7 goes into 22 3 times. Our remainder is 1. Our next division is 153 divided by 7. 7 goes into 15 2 times. And 7 divides into 13 1 time. Remainder 6. 21 divided by 7 is 3. Remainder 0. 3 divided by 7 is 0. Remainder 3. We repeated our division until the quotient 0 appeared. We're now going to write our remainders in reverse order. 7,508 equals 30614 base 7. Convert 9,583 from decimal to octal. Please remember octal means 8, so we're going to be dividing by 8. Doing my long division to the left. 8 divides into 9 one time. Into 15 one time. To 78 9 times. And into 63 7 times. Our remainder is 7. 1,197 divided by 8. 8 divides into 11 once. Into 39 4 times. Into 77 9 times. Our remainder is 5. 149 divided by 8. 8 divides into 14 once. And into 69 8 times. Remainder 5. 18 divided by 8. 8 goes into 18 twice. Remainder 2. 2 divided by 8. 8 divides into 2 0 times. Remainder 2. There's that quotient of 0 we were looking for. 9583 equals 22557. 9,583 equals 22557 base 8. We're going to convert 48 from decimal to binary. Remember, binary means base 2. So we're going to be dividing by 2. Careful here with your remainders. 48 divided by 2 is 24. Remainder 0. 24 divided by 2 is 12. Remainder 0. 12 divided by 2 is 6. Remainder 0. 6 divided by 2 is 3. Remainder 0. 3 divided by 2 is 1. Remainder 1. 1 divided by 2 is 0. Remainder 1. 48 equals, careful with your ones and zeros, 1, 1, 0, 0, 0, 0, base 2. Converting between bases other than 10. The rule tells us to go from the given base to base 10, then to the desired base. Convert 3164 base 7 to base 5. First, we're changing 3164 base 7 to base 10. So it's going to be 3 times 7 to the third plus 1 times 7 squared plus 6 times 7 plus 4. Multiplying and adding, it is 1,124. And I changed it to base 10, so it's okay to say it as 1,124. But now we want to change that number, 1,124, to base 5. So we will start by dividing by 5s. 1,124 divided by 5. 5 goes into 11 2 times, into 12 2 times, and into 24 4 times. 224 is our quotient, 4 is our remainder. Divide again by 5. 224 divided by 5. 5 goes into 24, 5 goes into 22 4 times. 5 goes into 24 4 times. Divided by 4, our quotient is 44. Divided by 5, our quotient is 44 and our remainder is 4. 44 divided by 5, 8. Again, remainder 4. 8 divided by 5. 5 goes into 8 one time. Remainder 3. And 1 divided by 5. 0. Remainder 1. We got that quotient of 0. So we're going to say that 3164 base 7 is equal to 13444 base 5. When conversions involve one base that is the power of another, because 8 equals 2 to the third, every octal digit can be expressed as a 3-digit binary numeral. Because 16 equals 2 to the fourth, every hexadecimal digit equates to a 4-digit binary numeral. We're going to use that chart we made with our binary our octal, our hexadecimal columns. We're going to convert 473 base 8 to binary form. 8 equals 2 to the third. 4 base 8, look at that chart, equals 100 in binary form. Excuse me, 100 binary form. 7 base 8 equals 111 binary form. 3 base 8 equals 011 binary form. So putting that string together, 473 base 8 is 100 111 011 in binary form. We're going to convert 8b4f base 16 to binary. 16 equals 2 to the fourth. So we're going to take each item and put it into its 4-digit binary form. 8 base 16 equals 1000 binary form. B base 16 is 1011 base 2. 4 base 16 equals 100 base 2. F base 16 equals 1111 binary form. Put it all together. 8b for F equals 1000. There was the cuckoo clock. Let's try again. 8b for F base 16 was 1000 1011 100 1111 in base 2 form. We're going to convert that binary number to octal form, base 8. Remember that 8 equals 2 to the third. So we're going to take that binary number and split it into 3-bit sections. That exponent of the 2 is a 3. Start at the right and break it into groups of 3, which is the exponent of the 2. 1 0 0 1 1 1 1 0. In binary, 1 0 equals 2, 0 1 1 equals 3, 1 1 0 equals 6. Put it together to get our octal form. 1 0 0 1 1 1 1 0 base 2 equals 236 base 8. Convert base 2 to hexadecimal. Hexadecimal is 16, and 16 equals 2 to the fourth. The exponent of 2 is 4, so we're going to split it into 4-bit sections. Start at the right and break it into groups of 4. Find the binary equivalents of those numbers. In hexadecimal, 1010 equals A, 1111 equals F, 0110 equals 6, 0101 equals 5. That binary number base 2 equals AF65 base 16. That is section 4.4, conversion between number bases.